Awesome. So we are now recording. All right. So for those who can make it, thank you for coming. Welcome to the third Leetcode Day. We're going over trees and like a short footnote on recursion. A lot of this is going to be complicated stuff, but I think we've done it in a way where it'll make sense. We have to brush over like some topics. Like I won't be able to go super deep into recursion because the reality is you'll learn it in like once you reach the end of programming 1 and programming 2, I believe. But we'll do our best with what we have. So yeah, let's see. Let me pull up my speaker notes. Awesome. So let's see. This is at the beginning of every meeting. I'm kind of going to brush over it. If you're watching the recording and you want more like detailed info, go to the first meeting. Basically, we're going to try and go through the 75 most useful Leetcode questions as curated by random people on the internet. Most of the meeting is going to be covering content related to it. We'll go over problems. And if you would like to help lead one of these sessions and you're an upperclassman with experience, or you just have a lot of interview experience in general, you can ping at Bob or at Greg. I meant to change that, but oh well. I'm also going to brush by this kind of quickly too. But basically, do the problems. Don't just watch this. Like pause when needed and actually take like 10 minutes to do the problems that are on the screen. Otherwise, like this will not be useful. I don't cover enough content in this for you to just master interviews, because this is only like a 30-minute meeting, an hour-long meeting sometimes. So yeah. What else? I'm not like the master interviewer. I've done really well in some interviews. I've done really bad in others. But like most of the people leading this are pretty comfortable with interviews in general. So, and we'll solve probably around 85 problems. We're going through a list of 75 and then adding a couple more as we go along. But 75 is probably not enough for you to just ace every interview without thinking, but it is a really, really good start. And once you get to like, in my opinion, once you get to like 150 good ones, then you're in really, really good shape for interviews. So this is the schedule. We've already gone through arrays and strings and linked list stuff. And some of those topics we'll cover after we take our off week on March 11th. But yeah, this is what it looks like so far. It's possible that our off week might be moved up, for those watching and wondering, but we'll see what happens. So yeah. So we'll get started with explaining what trees actually are. So a tree is an abstract data type. Technically, a tree is a type of graph, but we won't cover graphs in general until next week. But you can think of a tree as having a root, which is just an entry point, and it's one node, and this node has children, right? And so each entry point or node is either a leaf or an internal node. Now, leaves are the ones that are on the outside, excluding the root. So like you can see labeled here, all the ones that don't have children are leaves. And any node that does have children is considered an internal node. And then there's a bunch of random terminology that goes along with this that's kind of intuitive. So for example, this node is the parent of these two children. These two children are the parent, or these two children are the children of this node, obviously. Let's say you wanted to find the ancestors to this node. The ancestors would be this node and this node, right? So it's basically, your parent and any parents of your parent, if that makes sense. Let's see. So the links between these nodes are called edges. And all nodes except the root have one parent. So if you've been in programming 1, you're probably familiar with inheritance in Java. You can think of this as classes in Java. So I don't know, if you had an object class and it went down to a vehicle class, it went down to a car, motorcycle, bus classes, it'd be like that. And let's see, path link is the number of edges that must be traversed to get from one node to another. This definition is the general one. When you take data structures here, they might define it differently. And that's because if you took the path length from this node to this node, based on that definition, it would be 2, right? Be this edge and this edge. Now, depth is basically the path length of the entire tree to the lowest leaf, right? And these are all the lowest leaf, all these 3. So the depth based on that definition should be 2. Now, when you take it here, they'll actually tell you the height of this tree is 3. And that's because they do include the root node. Sometimes, like, some people do, some people don't. At UF, we usually include the root node. So when I talk about this tree, I'll say its height is 3. If that makes sense. Does anybody have any questions right now or not? It's kind of a quick intro to trees, but hopefully that made sense so far. That's a great transition. So a binary tree is a type of tree where there's only allowed to be 2 children max per node. And there's a lot of different takes on trees. There's a problem in the 75 problems we're going through that has you create a prefix tree, which we'll cover either next week or in a couple weeks. There's random other types of trees like red and black trees, which are really confusing, but really fast, which you'll learn about in data structures as well. Really, there's a ton of different trees, skewed trees, trees with fancy names that I don't know how to pronounce, but the most common one is a binary tree. So like I said, each node has at most 2 children, and you refer to them as a left and right child, right? And you'll see that in some of the syntax that we go through for the code. Now, a binary search tree is different than just a normal binary tree. A binary search tree is a binary tree where the left child is always less than the parent and the right child is always greater than the parent. Note that these are not examples of binary search trees. These are examples of binary trees. And we're going to come back to this slide later when we talk about traversals. As you can see, it covers like searches and stuff, but don't worry about it. We'll get to it. Any questions on what a binary search tree is or what a binary tree is? Incredible. Okay. So we have like a couple slides of vocab we have to go through. And this stuff isn't strictly necessary for solving Leetcode problems, but it's really good to know, like as you go into technical interviews and stuff, when you're asking about inputs and things like that. So a full binary tree is a tree where each node has exactly 2 or 0 children. This is an example of a full tree. As you can see, this would not be a full tree because this node has 1 child here. But in this, all nodes have either 0 children or 2 children. Okay, and then a complete tree is a binary tree in which every level except potentially the last level is completely filled. And the last level, if it's not completely filled, is filled up from left to right. It's kind of a confusing definition, but it's important because if an interviewer goes up to you and says, given this complete tree, where should a node be added in order to keep it complete, right? Now, based off this definition, does anybody have the answer to that question? The question being, where should a node be added to keep this tree complete?
Well, it's just on the left next to the other 3. To the right of the other 3 on the bottom. Yeah, right where your mouse is.
Yeah, you're correct. Yeah, if you put it over here, it's no longer complete. You put it here as the right child of this node, it is complete. So yeah, and that actually got asked to me one time, like at it was like one of the quick questions at a career fair, but just to make sure I knew what a VST was basically. So yeah, and then this also, you might not need to memorize for like Leetcode purposes, but it is good to know. A perfect tree is a binary tree with all leaf nodes at the same depth, 2 children on all eternal nodes. In other words, it's full and complete at once. So yeah, and those are, nice to work with. All right, I was tired of talking, so I'm glad we can move on. So this is like what a normal class for a node might look like. Depending on the Leetcode problem, they might give you different variations of this, but we'll just go through this one, for example. So obviously a node has a value. And in a lot of cases, like in the last slide, the value would be an integer. I mean, it can be anything, you know. And it has a left and a right node. And I mean, just as a simple constructor that allows you to give it a value, a left node and a right node, right? So when you want to access a node's left child, then you would do tree node dot left in Java. Same thing for the right. It'd be the name of the tree node dot right. Okay. Now keep in mind, 95% of the time, that'll look like root dot left and root dot right, because the entry point for any tree is a root. Okay. All right, so we're actually going to do this question kind of together. I don't think we need to break out into rooms since we don't have a ton of people. But we'll talk about it together, and I'll actually give you the answer afterwards, which I don't normally do. But I know this is confusing stuff if it's your first time. So question 104 is the maximum depth of a binary tree. So given the root of a binary tree, return its maximum depth, right? I also call this height. Technically, there's slightly different definitions. I don't really care. To me, they're the same. So the best way to approach this is through recursion. If you are a freshman, you may or may not know what recursion is. You probably do, I would guess, but it gets a little bit tricky with trees. So just to brush over it, you know, we could do a whole meeting on recursion if we wanted to, and you know, maybe we will if there's enough interest in it. But just to brush over, it's when a function calls itself, and it's really good for breaking up very complex problems into subproblems. And the most important thing to take note of when creating a recursive solution is a base case, right? So when you've actually finished a section of the problem. Most often in tree problems, this is when a node is now null, right? So you have tried to access the right child of a node, and it turns out it's null. That means you've gone too far. You're now outside the tree. And this will make more sense once we go through a problem. It might sound kind of weird right now. Now, a recursive step is the actual step you take towards the end of the problem. Most often in tree problems, it's just going to a node's left or right child. Okay. Now, a general rule of thumb, let me not get the pop-up in the way. You want to check if the input is one of the base cases at first. And if it is, you just return, you know, whatever the solution to the problem is. Otherwise, you perform the recursive step. So before we move on, you're given this problem. Does anybody think they already know the answer to this or no? If not, it's fine. We'll have it on the next slide. I'm going to take that as a no, and that's completely fine. So this is the actual entire solution, and we're going to run through this a little bit. I know it looks short, and it is, but it's kind of confusing conceptually. So let me go back to an illustration to help explain what this is doing. We'll do this one, sure. So let's say you're given the root node right here. And you want to calculate the height of this actual tree. What you would want to do is basically you would want to, maybe this isn't the best tree. Let's do this tree. Yeah, let's do this one. What you want to do is you would want to calculate the height of the left subtree and the height of the right subtree and find the maximum between those and repeat that for each node. So we would start with this node. We'd calculate the height of the left node. We'd be here now. We want to calculate the height of the left tree. We'd be here now. We want to calculate the height of the left tree. And each time you step over to one of these, you add one to the total of the height, right? So now you're here. Well, if you try and go one more, you're going to reach null. So that would be the base case, right? There's no longer a node there. So you return based off of the function that we created, which I'll show again in a second. And then you return that and you'd have an answer of 4. Then you'd go to the right subtree and go down again. You'd find it's null. You have an answer of 4 here as well. And then you return back up here. This would kind of repeat as you go along. I'm not going to draw through the entire recursive solution, but that hopefully walks you through it a little bit. So what this is actually doing is every single time max depth is called, if the node is null, then it returns 0. Otherwise, it adds 1 and tries to find a maximum between the left and the right subtrees, like we just said, basically. And so while this is like super short, it actually makes a lot of sense. And if once you go through data structures and algorithms, if you haven't been through that already, this will like become pretty intuitive for you, which is cool. So yeah. All right. So by the way, this is an actual Leetcode problem. So this is like one of the few times I'll actually give you the answer to a Leetcode problem. But these are the questions that we want to go through together in breakout rooms. Since there's only like 4 of us in here right now, I don't think that's necessary. What I would recommend is trying to do these 2. And if you're really confident, then do the other one. Sync tree is not difficult, and invert binary tree, I'll actually give you the answer to as well after this. So I'm going to pause the recording here. So if you're watching the recording, you should take 10 minutes and try and solve these 2. And if you're here, we'll actually go through this together. So, all right. So if you don't have time, that's fine. This is a solution to same tree. Basically, I'll cover it pretty fast, but the first base case, and we kind of went over it, but the base case is often when you reach a null node, it means like you've basically gone out of bounds with the tree. And if you've done that here, that means it's true, right? Because in any other scenario, it's going to return false already, right? So yeah, I think that makes sense what I said. But the only times this would be false is if basically one or the other of the nodes is null, or if the actual values within the nodes are not equal to each other, right? So those are basically the only 3 base cases you have to keep track of. And then in like the recursive call, it's basically just making sure that both the left subtree and the right subtree both are equal. So yeah, and you just basically call this on every node, and it works. So yeah, it's not too complicated, but it's just complicated conceptually, especially if this is your first time doing it. So like, don't beat yourself up if you weren't able to get it. And then the solution to inverting the binary tree. I think if you open the question, you'll see like the meme about it. But there's like a famous tweet about the guy who created Homebrew. He was asked this question in a Google interview, or he might be saying it facetiously, but he wasn't able to solve it, so they didn't give him the job. And it is true that he actually interviewed at Google and they didn't give him the job, which is wild. But yeah, so this is the actual solution to that. It's very similar. I mean, the comments kind of explain it, to be honest with you, but you're literally just swapping the left side and the right side of the tree. Now this swap method, this kind of abstracts away from what you'd be doing at a low level, but you can think of it as just creating a temporary node, storing the value of one node in there, and then switching the values. Kind of how, I mean, if you've been in programming 1 or programming 2, you've done it before, how to switch 2 values using a temp. So awesome. Now we're going to briefly cover traversals. We're not going to go through a whole lot of depth. Part of the reason why is because we're going over it next week anyways. And it's also a subject we'll keep on coming back to once we go through graphs. But I wanted to introduce you to the 4 main parts of traversals. So, and this is actually very important for most Leetcode questions involving graphs and trees in general. So a pre-order traversal is when you basically have the root pre, so before its 2 children, right? In order is when you have the root between its 2 children. So it's, it's in between both of them. And post order is when you're navigating to the root after navigating to its 2 children. Okay, so that was kind of a very hand-wavy description, but I'll give you an example. So, and before giving you an example, just to review what a traversal is, because actually I know some people might not be familiar, but it's basically when you're trying to reach every single node in a tree or every single node in a graph. Okay, So let's start with like a pre-order traversal. We'll cover level order in a second. The pre-order would be, let's say you want to print a pre-order traversal of this entire tree. You would start with the root that you're given, which is A, and then move on to the left child, which would be C. Now, this is actually the root of this whole little family, I guess you could call it. And so since this is the root, you actually move to its left child, which is F. Okay, so it'd be ACF. Then you go to the right child of C, which is G. So it'd be ACFG. Now you go all the way back up and you realize that you're done with the entire left node of A. So then you go to the right. Now, this is also the parent of this set of this whole family, I'll call them. So you print D. Then you go to the left first. This is the parent of this family, so you print H. Then you go to the left subtree K, right subtree L. You go back up. You need to check the right subtree of D, and you get J. Okay, and like I believe that's all explained correctly right here as well. I might not run through in depth all of them, but I'll go over in order as well. In order, you're given the root, but you want to start with the left subtree, so you go here. But this is the root of this family. So you go to the left subtree again and you start with F, right? Now, in order means the root comes in between the children. So you do F, C, G. And then you basically go recurse back up. This will make more sense once you see some code when I say recurse back up. But you see that the left subtree is done. And so now you want to go to the root or to the parent because it's in between the children. So it would be AFCG or FCGA, and then it'd be KHLDJ, I believe. So I think that's, yeah, I mean, you can check my work. So yeah, post order is basically the same thing. You just do the parent after the two children, right? I'm not going to run through that. Now, level order is a little bit more interesting, and it's actually relatively difficult to implement in code compared to the other three traversals. And we're going to cover it like in depth next week. I'm going to explain it now, but it is a pretty interesting solution and something that's a lot of fun to solve once you first start DSA at the beginning. So basically how it works is starting from the root, you want to go through each level in order of the tree. So a standard level order traversal would be A, C, D, F, G, H, J, K, L. Now, an interesting question that you'll be asked sometimes in DSA, but I'm sure you could probably be asked it in an interview. I don't know, or it'll be a weird question, but is A, D, C, J, H, G, F, L, K a level order traversal? You can chime in if you want. Otherwise, I'll just tell you the answer. The answer is it is. As long as the order in which you call each node in a particular level is consistent across every single level, it is a valid level order traversal. So if I even did A, D, C, H, J, G, F, K, L, that would actually be valid too. Very strange, but it would be valid. And in that pattern, you're basically going inwards right, inwards left, right? Actually, that would be LK. Sorry, on that last one. That's just good stuff to know because I have gotten one question where they made me do a really stupid traversal. I didn't do very well on it, but it was something like that. So yeah. So if we go to these problems, this is kind of the second set of things that we would want to cover. This one is pretty easy. It's very similar to the questions that we went through last time. It doesn't have to do a whole lot with traversals, although you can kind of use different types of traversals in that depending on how you want to solve it. 105, it says it's medium. If you haven't done a traversal before, it's probably going to be somewhat difficult. And 102 is a level order. If I remember correctly, the best way to solve that is with a queue. But we will cover this same problem next week. I'm just putting it on here so you know about it. And if this is your first time dealing with these types of problems, I'd highly recommend checking out Geeks for Geeks. I'll put the link in the chat, but it will show you how to do a standard pre-order, post-order, in-order traversal in code, and probably better than I could explain it, to be honest. But it's not going to give you the direct answers to these problems. You can kind of adapt what they have in there quite a bit and get the answers to these, but I would recommend going to this because it's not going to like reveal the solution to you. So if you're watching the recording, I'd recommend pausing and trying to go through at least this question. If you don't get it, that's okay. We're going to go over the answer to this question actually afterwards. And then these two questions, if you have time, you can try right now, but they'll also be homework. You know, get them done by the beginning of next week and you'll be on track. So let me pause the recording and try these problems. All right. So like 10 minutes or so is up. So this is the solution to the lowest common ancestor problem. I personally solved this in Python. This is not my solution, but it's the exact same. Basically, it's using the properties of a binary search tree in order to check for the lowest common ancestor, which it sounds like people in the reading actually came up with that same solution as well. So let's see. I mean, it's sort of self-explanatory. It's basically just going to continue iterating until it finds that lowest common ancestor, and then it'll return it once it reaches it, right? And the conditions are pretty simple. It's just checking if both the P tree and the Q tree are basically in the correct position, or I guess your pointer on the node is in the correct position yet. If it's not, it'll just keep recursively calling this method. So yeah. So in terms of problems for next week, once again, this always looks like so much, but it actually really isn't that much. So we solved this first one together. We solved the second one. We solved the third one. We solved this one. So there's really 1, 2, 3, 4, 5 problems on here. None of them are rated hard. I will say, if you haven't done a level order before, that might be confusing for a second. And kth smallest element is only hard until you realize how it works. But the rest of them are pretty standard. I would recommend, like for this pre-order, in-order one, like I mentioned, try and use Geeks for Geeks if you are really confused. But like that's a last resort. Try and do it on your own, obviously, at first. So yeah, I'll send these out in the Slack afterwards as well, which we haven't done before, but we'll start doing. Awesome. So thanks for those who could show up. Like I said, the slides will be posted, and I'll submit this form in the chat for you guys, and I'll stop recording. If you're watching the recording, we do these every Thursday at 7. So, you know, check out the Leetcode channel in the Slack and make sure to show up next time if you'd like to be here live and solve questions with other people. Awesome. Thank you.